Hello, I am Seema and welcome to part 4 of the chapter Organic Chemistry, Some Basic Principles and Techniques. As I told you that organic compounds are really very large in number. There are so many organic compounds that a separate branch of chemistry has been attributed to them, which is known as organic chemistry. These are basically compounds of carbon and hydrogen. They may contain other elements like you may have oxygen, you may have sulfur, you may have halogens, some other elements, nitrogen may be present in the compound. But these compounds, due to their extremely vast number and due to their properties really depending on their structure, it becomes very important to write down the structures and to know the structures of these organic compounds because their properties would mainly depend on their structures. But then the next problem that scientists have or chemists have is that if we need to know the structures, how do we convey the structure from one person to the other in a book and not really actually having to see the structure? How do we write down these structures? So the way we represent these structures, there are different ways how we do it, and it becomes really important to know how do we represent and what do these structures mean. So the topic of this video is going to be structural representation of organic compounds. How do we write down their structures? You have studied even in lower classes, and you've studied, that is in class 10, and you've studied about the Lewis structures. In Lewis structures, what we do, we write all the bonded atoms in the correct sequence, that is which is bound to which, and every bond is represented by a pair of electrons. This pair of electrons is shown by two dots. So in a covalent bond, it is assumed that each atom is contributing one electron. So one electron from this atom, one electron from this atom, both the electrons would result in the formation of a covalent bond, which is represented in the Lewis structure by two dots. So the very first way how you would represent molecules would be by Lewis structures. So the Lewis structures, in Lewis structures, what do? Hydrocarbons mainly consist of carbon chains. So we first write down the carbon chains. We know carbon is tetravalent. So every carbon should form 4 bonds. So these 4 bonds are represented by 4 dots around the carbon atom. And these 4 bonds, who is it forming those 4 bonds with? Is it forming the 4 bonds with 4 separate atoms, or is it forming a double bond? Based on that, you place the dots. For example, you have ethane. In ethane, there are 2 carbon atoms and there are 6 hydrogens. So each carbon forms 4 single bonds. It is a saturated hydrocarbon. So you notice here, each carbon, both the carbons are joined to each other. Therefore, the chain consists of, the 2 dots are drawn here. These are the 2 carbons, and each carbon is attached further to 3 other hydrogens. So represented by 2 dots each. So you have CH3, CH3. That forms ethane. But in Lewis structure, how are you representing the bonds? Every bond is shown with the help of 2 dots. In case of ethene, you have a double bond between the 2 carbon atoms. Therefore, we put for each bond, there is a pair of electrons. If there are 2 bonds, there will be 2 pairs of electrons. So you have 2 electrons being contributed by this carbon, 2 electrons by this carbon, and thus it forms a double bond. When you have 4 electrons between the 2, it shows that it has these 2 atoms share a double bond. So one of them is a sigma bond and the next is a pi bond. And the 4 hydrogens, of course, are forming single bonds, which are shown by a pair of electrons each. So this is how you would show Lewis structures. If you had, let us say, ethyne, how would you represent ethyne? In the case of ethyne, you will have 3 pairs of electrons between the 2 carbons, and there would be only 1 hydrogen each on both the sides. Let me just draw ethyne. Ethyne would be between the 2 carbons, you will have 3 pairs, and 1 hydrogen here and 1 hydrogen here. I'm just making it a little smaller due to the little space that I have. So you have 3 pairs of electrons, which means there is a triple bond between the 2 carbons, and with the 2 hydrogens you have single bonds. So that is the first way of representing organic compounds by Lewis structures. In Lewis structures, we make the electron dot structures. They are known as electron dot structures because here the shared electrons are represented by dots. And even the lone pair of electrons are represented by dots. The second is a complete structure. It is known as the complete structure. What do you do in a complete structure? In a complete structure, we do not use dots because it takes a lot of time to make individual dots. But we use dashes. So a dash is easier to make. So whenever you have to show a bond, you show it by a small dash. So we come back to the same molecule. Now ethane would be represented by CC. There's a single bond. All the hydrogens have got single bonds with them. Ethene would be with a double bond, and these are single bonds with hydrogens. Ethyne would be carbon-carbon triple bond and two single bonds with the two hydrogens. So this is a complete structure. A complete structure is one where all atoms are written in the form of their bonding, and the bonding is shown with the help of dashes. But lone pair of electrons are represented by dots. For example, in methanol you have carbon forming 4 bonds, 3 with hydrogen, 1 with oxygen, and oxygen forming a single bond here with hydrogen. But oxygen has 2 lone pairs of electrons which are represented by these dots. A pair of electrons represented by a pair of dots here, and another pair of another pair that is a lone pair of electrons here. So it has 2 lone pairs of electrons. So this is a complete structure. As we go on to other structures, we could use even larger molecules. For larger molecules, you can see if the molecule is larger than this, you would have, let us say you have 3-methyl octane. If you had 3-methyl octane and I had to write down the complete structure for 3-methyl octane, I would have to make a really giant molecule. I would need a lot of space. There would be 8 carbons in sequence, all hydrogens filled up like this, and on the 3rd carbon I would have the methyl group where that carbon will further form 3 more bonds. So it would be a very expanded structure. So the complete structure is when you want to represent exactly where each bond is. But then this is assuming that the person who is reading does not actually know that hydrogens would be bonded. When you understand it a little better, you know that every carbon forms 4 bonds, and we are writing down organic compounds which are compounds of carbon and hydrogen. So it is not necessary that we actually show each and every bond. We can assume that whatever the carbon chain is forming, wherever you have multiple bonds, there you may have to write down the dashes. But wherever there's just hydrogen filling up the rest of the vacancies or the valency, you just write the hydrogens. So that is done in the next structure, which is known as the condensed structure. You are condensing it. You're not writing every bond. You don't, because it is understood. Some of the bonds are, there's a carbon chain. So every carbon is bound. So there is no need of putting a dash every time. You know that carbons are attached to hydrogens. A carbon which is on the end will be attached to 3 other carbon atoms if it is a saturated carbon. sp3 hybridized. But if it is in the second place, that is, it is attached to 2 other carbons, obviously it has a valency of only 2 valencies are satisfied, you are left with 2. So being tetravalent, you have 2 more valencies, which will be filled up by hydrogen. So whenever you have carbon which is in the middle of the chain, it is attached to 2 other hydrogens. So it would be CH2. If it is on the end, it will be CH3. If there is a double bond or a triple bond, then obviously from both the carbons, one hydrogen will be removed, because it is that pair of electrons which is being shared. So condensed structural formula, how do we write the same molecules? Here you have methane. In methane, I have written CH3. I have on purpose written the dash between the 2 carbons because this is a small molecule. You're not really wasting a lot of space, and writing just 1 dash is not difficult. But when you come to a larger molecule like this, you can avoid writing the dashes between the carbon atoms too, because that also is assumed that the person who is writing it or reading it would be understood to him. So this is ethane, this is ethene. In ethene, now what is the Where are we putting the dashes? We are putting the dashes where there's a single bond between two carbons, there's a double bond between two carbons, there's a triple bond between the two carbons, just to specify how many bonds are there between the carbons. And the rest of the valencies are filled up by hydrogen. If there is only a single bond between two carbons, they would be, to complete 4 valencies, you need 3 hydrogen, 3 plus 1, 4, 3 plus 1, 4. If you have 2 bonds already, then you 2 are already there, so you need only 2 hydrogens, so CH2. So in other words, when you're writing down the formulae, you automatically kind of know what you are supposed to write. If there's a triple bond, 3 valencies are already fulfilled, so you need only 1 hydrogen, so that would form ethyne. And methanol then would be CH3OH. We do not specify the lone pair of electrons because this is a condensed formula. You would again know that oxygen has 6 electrons in its outermost shell. Obviously, if it is forming 2 bonds on the 2 sides, then it has 2 lone pairs of electrons which are still available to it. Then comes a little more, a larger molecule where a condensed structural formula makes sense. That you have CH3, CH2, CH, CH2, 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 CH3, and at the 3rd carbon you have a CH3 attached here. It is 3-methyl octane. Now, when this has been condensed, we have avoided all the dashes except for this one where we are showing a branch. You can further condense a condensed structural formula. When you have a long chain of CH2, CH2, let us say I had 20 CH2s here. Would I keep writing the CH2, CH2 20 times? Rather than doing that, I would just put a bracket. I'll write CH2 once, I'll put a bracket and I'll write 20 outside it as a subscript. So what have I done? Instead of writing, a long chain, I've just condensed it further. Now, take a look here. Here you have, after this CH, how many CH2s do I have? 1, 2, 3, 4. So I have 4 CH2s. I don't have to write all the 4 CH2s. If I want to further condense it, I write CH3. Now these two are different, so I can't condense it further. You can only condense it further when you have a similar group or a similar group of atoms which is being repeated. There you can use a bracket and then put a subscript. So CH3, CH2, CH, CH3. This is very distinct. There is no repetition. But the CH2s have been repeated 4 times. So I'll put a bracket. I'll write CH2 only once. I'll put a bracket and I'll say there are 4 CH2s. And then it is followed by a CH3. So that is how you would condense even a structural formula. This is a complete structure. You condense the structure and then you can further condense the structure by putting a bracket and writing multiples of that outside the bracket when you have a large molecule. The next structure is bond line structure. Bond line structure is going a step further, We know we are talking of organic compounds. We know we are talking of carbon and hydrogen. So the next thing is that it takes time to write C, it takes time to write H, why do I not simply eliminate this? I know that carbon would be at the end of this bond. If I just imagined these 2 lines to be there, I know that this would be a carbon and this would be a carbon because I know I'm talking of hydrocarbons, and if there are 2 bonds between the 2 carbons, it is understood that the other 2 would be hydrogens. So why do I have to write the CH2? Why don't I just put lines? Such a representation was known as the bond line structure or the bond line notation. What do we do in bond line notation? We make the bonds between carbons. On purpose, we make the bonds between carbons, and here there is a twist, We are going to eliminate even the carbon and hydrogen, the symbols. And since we are going to eliminate this, if I had to write this structure, let us say, in a straight line, and I was not even writing the CH2, and just showing the bonds, I would have made 1, 2, 3, 4, 5, 6, I would have gone like this. And on the 3rd, here, I would have shown a branch here. This would look so strange. It would be a little confusing. So what do I do? In order to simplify this, I do not write it in a straight line. Rather, I write every CH2 or CH3, and the dashes that I make are zigzag. I make them in the form of a zigzag, because when they are in the form of a zigzag, counting them becomes easier. You have a pair, 1, 2, 3, 4. So counting becomes easier. So here I write CH3 and I show a dash for the next. The carbon bonds are shown by a zigzag. And when you have a branch that comes out of a carbon, that is also shown by a dash. Now the bond line structure, actually you achieve it when you eliminate even these and just make the bonds. So this end where you're just making the bond, what does it mean? What does an empty end mean? An empty end means it's a CH3. I've made the same structure here. So any joint, what does it mean? A joint means it's a CH2. So this is a CH because there is a branch here. Since there's a branch here, this would be a CH. It's understood. This is a CH2, this is a CH2, this is a CH2, this is a CH2, and since this is the end will be a CH3. So I did not have to write any of the symbols, yet just by knowing whether it is the end of the structure or is it a joint of the structure and how many offshoots are coming off a joint, you can tell how many carbons, one carbon of course at every joint, and how many hydrogens would be there. And every open end is a methyl group. And if you have oxygen, then of course any atom which is other than carbon and hydrogen would have to be written. Let's say you have nitrogen somewhere, you have oxygen somewhere, you have a halogen, those symbols will have to be written. If you had a chloro, let us say, yeah, here you have bromo, so you write the bromo. The only atoms that you would not write would be carbon and hydrogen, assuming that the person who's reading it and the person who's writing it knows how many carbons and how many hydrogens would be there. So what do? Basically, we are making our job simpler. As our understanding of the carbon compounds increases, we make the structures even more simpler. For example, if I'm sitting and I'm making my notes, I would not want to waste my time writing down these structures. I would like to just do this, and when I come back to it and refer, I already know what to expect here. So I would easily be able to identify the molecule. So this is for example, you have 2-bromobutane. And you have to write 2-bromobutane in different ways. So 2-bromobutane can be written as this condensed formula, that is CH3, CHBr, CH2, CH3. You could write it as the expanded formula also. How would you write 2-bromobutane? If I wrote it, I'm not writing as Lewis structure, as the complete structure. CHHH, so I write CH3, CHBr, CHH, CHHH. So that would be the complete structure of 2-bromobutane. Then this is the condensed structure. The next one is the bond line notation, where I have written although I've made it to the next step, that I've written down the symbols of the carbon and hydrogen, but in the final one, I have come to the actual bond line notation, where I ignore even the carbons and hydrogens. I only make the bonds. So I get the structure. Similarly, if you have cyclic compounds, then bond line notation is really very commonly used in cyclic compounds, because just by looking at it, a quick glance, and the geometry kind of fascinates the eyes more than complex structures. If you just look at a triangle, a pentagon, or a hexagon, you'll quickly know how many carbons are there. Triangle, there are 3 carbons. A square would be 4 carbons. Pentagon would be 5 carbons. A hexagon means 6 carbons. So in cyclic structures, this bond line notation makes it so easy to make the structures, because you only have to make these geometrical structures, and the rest is just your knowledge that will tell you how many. And remember, when you have a cyclic structure, all corners have got 2 lines. It means that the carbon is forming 2 bonds. So how many hydrogens would be there to complete the tetravalency? 2 bonds it is already forming, so it will have only 2 hydrogens. So look at this, CH2, CH2, CH2 is cyclopropane. Each one is bonded to the other 2, therefore you get this cyclic structure in the form of a triangle. In cyclopentane, you have CH2, 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 and you make it in the form of a pentagon, because that becomes easy for you to understand. And cyclohexane, you would make it like this. It's cyclic. It is chlorocyclohexane. So you have chloro at one of the carbons. So that, of course, whenever you have an atom which is other than carbon and hydrogen in the bond line notation, you have to write that one. So here I've written chlorine. Right? So this was the structural representation of organic compounds. In the next video, we'll do the solved examples just to get a little practice of this, and then we'll proceed further in the chapter. If you found this video helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.